Hello and very warm welcome to this today's live training session on testing an inverter with E-Motor Emulator based testbed. In today's agenda will be to inform and introduce all our audience to our company, which is presently known as AVL SET, and what we are, where we are located, what are our core competencies, and so on. We will introduce you to that aspect in the beginning of the presentation. Then I will speak about the conventional inverter test setup, what they can offer, what are the shortcomings, and what are the requirements of a drive inverter test requirements, and so on. And then I will introduce you all to our emulator-based inverter testbed, what are its key components, core constituents, what it can, and so on and so forth. And then I will briefly introduce you to the most interesting factor or today's main key point. That's inverter test enclosure, what it is, what it consists of, what can it offer for facilitating testing of an inverter. Then I will briefly demonstrate you with the help of a video how easy and hassle-free it is to install this test inverter into the E-Motor Emulator based testbed. Then we will speak about the key interfaces. What are the key interfaces which are available for connecting the inverter? And then we will check what is RPS, rotor position sensor, how to connect it, how to check its functionality, if it's working or not, and so on. And then we will see how we can emulate an intended motor model. So the emulator is ready, so it needs to emulate a particular e-motor, electric motor. So how we can achieve that, I will introduce you to that as well. And then once the inverter is installed, the position and safety limits are checked, then we need to check how we can assure and adjust safe limits for the testbed itself so that it can assure the safety of the inverter as well as the testbed. And then the presentation will end with a summary. So this is VR. We are currently known as AVL SET GmbH. We are currently located in a southern city of Germany. It's called Wangen. It's 200 kilometers from Germany. So the company started as SET Power Systems, which was a pioneer or a key player in the field of e-motor emulation for aerospace industry. And a joint venture was established between AVL List and SET. AVL is a well-known player in global automotive market. And then the SPS Smart Power Systems was established in the year of 2012 as a joint venture with approximately 5 employees. So the main concentration or core segment of this joint venture was to provide e-motor emulation solutions for testing automotive inverters. And then in the year of 2019, the company was renamed to AVL SET. So we are proud of the fact that we are the market leaders currently providing the e-motor emulator test solution, or also known as power hardware in the loop test solutions for testing the drive inverters. So we are proud of the fact that also our top customers are the top automobile manufacturers worldwide. So that is briefly about us. Let's see what our competencies are. So for a drive inverter testing or an inverter test requirement requires certain key performance aspects, such as high performance, high switching frequency, power architecture, so that the required amount of current can flow in the power loop ripple free. So we are capable of such a power architecture which is capable of switching at 800 kilohertz and capable of handling more than 1200 ampere, and it's still modular. One can modulate it up to operate even more than 1200 amps and can operate at a DC link voltage of 1200 volts. And the next requirement to emulate a more realistic physical behavior of the motor model, it's necessary that ultra fast computing platforms and a real-time motor model is necessary. So we provide our customers with 3-phase, 6-phase permanent magnet synchronous machine, asynchronous machine, or also known as induction machine, and externally excited synchronous machines, which is emulated and working at a very fast model iteration speed of 320 nanoseconds, and it's almost quasi emulated in quasi real time. So we also provide or facilitate automation and an ultra-fast instrumentation. So this is also one of the requirements for dry inverter testing, where the data acquisition rates are really high. So we provide voltage acquisition system at 25 megasamples per second with an accuracy of plus or minus, with a tolerance of plus or minus 1%. So what are the inverter test competence we offer? So the calibration tests, endurance tests, performance and analysis and robustness tests, and also reproducible fault scenario and fault injections. These are the few of the core competences which we offer to our customers under one roof. So now let's have a look at the requirements of a conventional, the requirement of an inverter testing, and also what are the conventional solutions which are available at the moment, and what they can offer, and what are the shortcomings. So, from our experience and the market analysis, we have established that in order to test a high voltage battery, there is an established battery test system. To test an electric motor, there is a dyno or E-motor testbed, with which one can test the E-motors. But is there a full package solution to facilitate all the requirements of inverter testing? So here are some of the aspects which I have compiled here, which are available classically. One is the signal hardware in the loop. In this case, actually, the actual required amount of power will not flow through in the system. It's just a signal level modeling where one can only validate the functionality of the controller, or signal acquisition and calibration and so on. But actual power doesn't flow through, so one is not able to validate the performance or thermal analysis of the said inverter. Let's say we have a choke with which one can test a block rotor test, where there won't be any back EMF. It's just a current flows through, but however, the power is only ohmic power in that case, where the chokes represent ohmic inductive network of a particular motor, but still there is no active power flowing, and there is no bidirectional operation possible with this setup also, which is one of the most important requirements. And then let's say we go to dynos, it's also known as E-motor testbed. One should not confuse with E-motor Emulator based testbed and E-motor testbed. Here, E-motor testbed implies it's a dyno based testbed. In order to do this test, one should have a motor already beforehand to test a particular inverter in combination with this motor. So you cannot vary the motor beforehand. So in the development cycle of this particular said inverter, if the motor is not available, then it's not that easy to validate all the functionalities of the inverter and also cross-correlate with the parameter variation or motor parameter variation. And fault stimulation, such as breaking of shaft or extremely high-speed operation, curb stop or hill climbs, such scenarios cannot be easily facilitated with this dyno-based test setup. And as I said before, there are also dyno influences which could also affect the test results of the said inverter itself. One can also go to the vehicle directly and start testing there, but the cost will be really high, and it is under the assumption that the vehicle is already there and all the test phases have been completed, so which will be very expensive if a fault is found on the later stage. So these are the requirements. Now let's see whether we can solve this problem with less expense or facilitate a rapid development cycle where one can validate all these said test scenarios beforehand. So now for this solution, the said solution, we can use E-motor Emulator, which facilitates all aforementioned test requirements. Now we can look into how this E-motor Emulator based testbed looks like. So if I can draw your attention to this particular picture, what you see on the screen right now. So here is the most interesting part, where this is called as inverter table or inverter enclosure, where we place the inverter to be tested here safely and very easily, which I will show you in my subsequent tests. So this particular inverter needs to be supplied with a DC power supply. In this case, it could be a battery or a battery emulator. So the battery emulator is placed here, so there will be a DC power supply to the inverter. And then on the background here, we see this is the emulator, E-Motor Emulator, Electric Motor Emulator. From now on, I will use the word EME as a short form for this Electric Motor Emulator. So this E-Motor EME consists of a control cabinet and a high-performance power architectures, which are capable of handling currents more than 1,600 ampere here, because since it's modular, in this figure, it's only a representation for a one configuration matrix. And then here is the possibility to inject or stimulate various fault scenarios, such as short circuit, face-to-face shorts, or phase open shorts. All of them are possible at high voltages and high currents, and they are all 100% reproducible. So the the emulator also requires a DC power supply, which is provided with the DC supply cabinet here. And then only one host PC can control both the inverter as well as the emulator, which makes the job of the tester very simple and easy. And optionally, we also have a e-power analyzer, which facilitates data acquisition and analyzing your all test results, on which there is one more webinar available from AVL SET in these on these live training sessions. Users can also look into that for further details. So this test system or test bed also facilitate automation. One can also automate your test sequences, long duration tests or various test scenarios can be automated entirely with the help of a Puma inverter, which is also a solution provided by the AVL, or customer can also use his own automation system, which is easily integrated with our control flow. So let's look into the inverter enclosure, what it looks like. So here is the brief overview or background view of inverter enclosure, where one can see a test inverter is already mounted, which ensures the safety for the device, which consists of a smart safety control system, which ensures that the doors are stayed in locked position, and it is also automated when the user is testing this particular inverter with high voltage. So that's safety part. And secondly, there are easy connection terminals, which are plug in and play. That is just that easy to connect the inverter to the DC side, and also the signal interfaces and cooling units and so on. It also additionally comes with a discharge unit, which helps to rapidly discharge the said inverter or the connected inverter after a high voltage test, so that it can be easily demounted to carry out further needed activities in the testbed itself. And it also comes with a low voltage DC power supply to provide this particular inverter with the control power supply, so that the controller can operate. So let me introduce you to the concept of e-motor emulation briefly, and how one can test the inverter without actually having a motor beforehand, while emulating actual behavior of the electric motor. So as I mentioned, there are two concepts available. One is our grid power cycle, and there is a DC power cycle. So let me start with grid power cycle. So the grid power cycle structure looks like this. There are two power supplies. One power supply for the emulator, where it provides a DC, high voltage DC power supplies to the emulator cabinets. And there will be another power supply for the inverter, which is also capable of emulating the behavior of an actual battery. One can also parameterize to behave it as a required battery. And then when the emulator or the motor itself acting in a generator mode, the power will be flowing from emulator to the inverter, and the cycle will be completed over the grid. So as we look at this, why this requirement is necessary, why over the grid cycle? So this is needed because it facilitates the user to use an actual battery to be included in the test loop. So that is one of the added advantage. And then next, what are the key requirements to start the test? All we need is a resolver, which is a different type of a rotor. All we need is a different type of rotor sensor emulators. We also provide resolver, XMR, Hall, or encoder sensor emulators, which we connect, which is directly integrated in the emulator itself, which provides the rotor position signals to the inverter and three-phase connection. That's it. And similarly, if we compare it to the DC power cycle here, there will be only one testbed supply cabinet where it provides a DC power supply to the inverter as well as emulator directly from one source. With this, a hardware footprint can be reduced considerably as compared to the grid power cycle. However, an actual battery cannot be used in this DC power cycle scenario. So the other connection requirement or interface requirements still remain the same. It's just this principle, three-phase, three-wire connection between the emulator and the inverter, just as we have it in a real inverter and the motor, and a signal connection between the resolver or rotor position sensor emulator to the inverter. That's it. So now, if this setup is done, the connection setup is ready. Now let's look at in detail how we can install this inverter to the inverter enclosure and make it ready for high voltage testing.
Hi, in this video I will demonstrate how we can install a test inverter inside the inverter test table and make the necessary connections to the E-Motor Emulator on the high voltage side as well as the signal interface side, so that we can test this inverter with our E-Motor Emulator based test bed. So here I have three-phase AC connections from the inverter, DC plus and DC minus high voltage terminals which needs to be connected to the high voltage power supply, a potential earth cable to potentially ground this particular inverter, a signal interface to connect the inverter to the required resolver or rotor position sensor. In this case we are going to use the resolver. We have one more low voltage power supply connectors here. In order to supply this inverter with low voltage power supply, we have this connector and we will make a connection. And then we have a control interface between the inverter and to the control PC, and also a water cooling circuit connection for this particular inverter, which needs to be connected with the cooling unit, for which we have the terminal inside this particular inverter. These are the two DC plus and DC minus cables coming from the inverter. Now I will connect them to the high voltage DC power supply terminals on the inverter table here. Okay, so these are the three-phase AC cables, and then I will connect them to the three-phase AC terminals of the emulator, which are terminated here on the inverter table. Now I connect the potential earth, or I will connect the body of the inverter to the potential earth, to our potential earth bus bar here. Okay, now I will do the signal side interface one by one. A resolver connection to the CAN interface, and low voltage power supply. And finally we connect the water inlet and outlet so that the inverter can be cooled.
So I hope this video helped you to understand how easy and flexible and hassle-free it is to mount a test inverter into the inverter enclosure and connect it to the emulator testbed and and start with the testing. So now let's look at the key interfaces. What are the key interfaces which we need to consider before we start the testing? So the power side cables with the 3 phases needs to be connected to the 3-phase terminals of the emulator, phase U, V, and W. So it's easily terminated here. One can easily mount it. And secondly, the DC side cable also for the inverter to be supplied with the high voltage. And the signal side interface, we need only a signal from the rotor position sensor. That's it. And then low voltage power supply, and then the CAN interface. All the other aspects of the safety and other protocols will be taken care by the emulator control software itself. So the user has to take care of only these 3 key interfaces, and yeah, the inverter should be ready to start the test. That's the idea. So now let's look at, so we connected the resolver, so rotor position sensor. In this case, I'm taking an example of resolver as a used rotor position sensor. Let's see how we can test its functionality once connected to our emulator-based testbed. So once we open the emulator control window, this window pops open. Now I am already in the signal scope tab, where I have already plotted 2 signals to be visualized. One is rotor speed and the other is the rotor position. If I can draw your attention to the left-hand side, where one can command the required rotor speed in RPM for the motor, which is emulated, and then also the rotor position. Here, with just one click of a button, we can block the rotor at a predefined, precise position of a rotor. So right now they are all frozen, and now they're at 0 speed. And additionally, I can also set a rotor acceleration limit as well. So before we do that, we need to parameterize the selected rotor position sensor. In this case, it's resolver. For this resolver to be parameterized correctly so that it can emulate actual behavior of the intended rotor position sensor or a resolver, we need some key information such as transmission rate of the used or the set resolver, then the number of pole pairs, and the signal gains of sine and cosine components, which are the amplitude modulated components, which can be parameterized directly from this parameter tabs here. Additionally, this resolver emulator can also emulate behaviors such as fault stimulation. We can also stimulate faults. We can also include this resolver signal to include some sort of noise, such as Gaussian noise or pink noise with a predefined noise amplitude. And also we can include a spike with certain frequency and spike amplitude. Now I will demonstrate how we can parameterize them one by one. I've taken an example of a resolver which we use here for our testing. So it has a transmission rate of 50 and a pole pair of 1, and it requires a sine signal gain of 100 and cos gain of 100. So that's it. My resolver is parameterized. So if a user wants to parameterize another resolver, then these parameters can be easily changed. Now here I am setting up a rotor acceleration limit, where when you command a certain speed, this speed can be controlled at with which rate it can increase or decrease. So the higher the value, the faster the rate of rise of the speed. The slower the value, the vice versa. So I can set a value to 100 degrees per second squared, or even higher value. So that's it. Then now I have parameterized this value, and then we'll command the speed of 1000 RPM, and then I'll unfreeze the position and hold the speed at a constant value. We can see the speed rose to 1000 RPM, and we can see the rotor position here, which is seen on the scope window here. And then we need to confirm the same signals, the speed value and the directions are also reflected on the inverter side, if the inverter is also reading this value or not. This is one of the key factors which we need to verify beforehand. We can also see this is the graphical user interface for the said inverter, where I have plotted the speed and the rotor position. This is also reading the correct position and correct speed with the correct magnitude and direction. So let's see what happens when we change the direction of the speed. So now I'm changing the speed direction to minus 1000 RPM and the speed direction reversed. So minus 1000 RPM, and similarly, we can see the same value here on the inverter. It is reading the correct value, minus 1000 RPM, and also the rotor position. So this means the rotor position sensor, in this case a resolver, is connected properly and configured correctly, and the communication is correctly established between the AMA as well as the inverter. So now we successfully installed the inverter and we successfully connected the resolver or the rotor position sensor, and we also checked the functionality. So now we want to know how we can emulate an intended motor. So from our side, the AVL SCT provides these motor model types: permanent magnet synchronous machine 3-phase, 6-phase, externally excited synchronous machine 3-phase, 6-phase, and induction machines 3-phase and 6 phases. So our motor models are completely generic, but accurate and precise, and completely governed by physical and electromagnetical equations, considering also the required effects as we would see in a real motor, such as magnetic saturation due to ion saturation in a real motor, and also cross-coupling effect due to which a flux change, we can see it in the D and Q components of the flux because of the changes in the currents of D and Q components. So for the motor modeling, I have taken an example of 3-phase machine PMSM here. These are a few of the considerations before assumptions or considerations we have carried out before we model the motors. The rotor is symmetrical to the D-axis, and three symmetrical windings connected in star formation, and star point is not connected. Capacitive displacement currents and skin proximity effects are not considered. And also, the reason behind making this models generic is that to reduce for the customer the modeling effort and save the time, and make these models very accurate and precise, and should not be tweaked just to see a required behavior. So the motor should always be governed by these physical and electromagnetic equations, and only the behavior should be changed, or as and when, depending upon the inputs what we define. In case of a linear model, as I said, cross-coupling and so on, and then in case of non-linear model, saturation and cross-coupling. And we also have a model depth, which is non-linear model with other dependencies, such as harmonics, where it depends on the rotor angle, temperature effect, where user can specify a temperature for permanent magnet or stator, with which the behavior of the motor also changes. And also the user can also define a third dimension, with which also flux linkage maps are dependent. So the idea is motor is generic. A user has to only provide the data for the motor and no need to emulate the motor itself, so that the exact behavior is maintained throughout. So how can we get the data? For a linear model, we can start with analytical calculation and start with linear model. If you have an inverter already designed, which knows to be used with the intended motor, from which also we can derive the model data for the linear model and non-linear model. And with tools like ANSYS, one can do a finite element analysis and extrapolate data for nonlinear temperature, nonlinear harmonics, and nonlinear user-dependent dimension. With the finite element analysis, could be possible there will be a variation with an actual motor. So in order to validate that, one can connect the motor, once the said motor is designed, connect it to a dyno and start extrapolating the model data again and cross-verify it with the model data which was acquired through the analysis. So as I said, model calculation is quasi continuous in real time, and whole model iteration speed is 320 nanoseconds, which helps representing model behavior almost equal to the physical behavior in quasi-continuous domain. So now we know how we can get the motor model data. Now let's see how we can parameterize the E-Motor Emulator to emulate this said motor model. So of course, the information regarding the modeling and motor model data acquisition is not whole complete in this particular webinar, but in our in this live training, in our upcoming live training session, it will be dealt in detail. So please stay tuned and subscribe to our newsletter to get yourself informed in future cases. So let's now look at how we can parameterize a linear three-phase PMSM motor model. So once we open the AMA client window, so this plot window opens. Now we switch to the motor model tab, where we can parameterize and select different types of motors and parameterize the required values. So right now, on your screen, you can see a linear model mode is selected, and a motor model type is PMSM three-phase. With a few click of a button, you can switch between the motor type itself, three-phase, six-phase, or induction machine. So I'll stick to the three-phase PMSM, and I can also change the linearity or non-linearity from this tab here. For parameterizing the linear motor model, we need only 5 parameters: permanent magnet flux, self-inductances in BQ domain, stator resistance, and pole pair. That's it. And here, what the other parameters what you see are relevant for emulating temperature-dependent behaviors and so on, which will be dealt with in our upcoming live training sessions. So let's start parameterizing the motor model. In this case, it has a permanent magnet flux of, let's say, 0.02 volts per second, and the self-inductance of 200 microhenry, and the self-inductance in Q domain of 600 microhenry, and a pole pair, stator resistance of 10 milliohms and pole pairs of 4. That's it. My motor model is now ready. It's parameterized and it is ready to be emulated. So now the inverter is mounted. It's correctly interfaced. The rotor position sensor is connected, and intended motor model is also parameterized. Now we need to consider what are the safety limits that needs to be considered beforehand. As I said, we have 2 power supplies in the system for emulator, one for the emulator and one for the inverter. So they each have a maximum power, DC power limits. So that needs to be taken care of beforehand. These values are usually preset by us, but depending upon the requirement of a test case, one can adjust these values easily to a lower value or below the maximum allowed value. And also similarly, the DC link voltage for from the battery emulator to be tested with the inverter. If you can operate an inverter from 0 to 1000 volt. Depending upon this, you can specify a safety limit with which the inverter should operate. And similarly for the power for the EMA, and also the DC link voltage of the EMA as well. And then one key factor is a maximum current limit that needs to flow in the power path. So depending upon the number of power architectures we have, the configuration assumes a different preset maximum current limit. So that needs to be taken care of, or it's taken care by us. Only case is you need to specify a allowable safety current depending upon your test cases, which an inverter can handle. For example, if we have a emulator which is capable of handling 1600 ampere, but the inverter is only capable of, let's say, 400 ampere, then this value can be tweaked easily with this allowable phase current limit, and that's it. It ensures the safety of all the power supplies, the emulator, and also the UT itself. So additionally, once the safety limits are considered, now we come to the fact how we can command some torque safely. So for a given synchronous machine, permanent magnet synchronous machine, this is a very well-known picture, I assume. I assume we would know a corner speed of the machine, and we know how many power architectures we have. So always up to the corner frequency, one can achieve the rated torque, but one has to keep in mind the maximum RMS current is well below the maximum limit set, which is preset. And additionally, above the corner speed, the torque should be less than or equal to the total power divided by the speed of operation at that instance. So to summarize this entire presentation, I demonstrated how easy and hassle-free and flexible it is to install this inverter, how one can switch between different motor type and parameters within few seconds, and how one can see a rotor position sensor can be connected and its functionality can be tested. What are the features available, arbitrary electrical faults or mechanical faults which we can emulate with this system, and the safety features in terms of safe limits for the UT as well as for the emulator testbed itself. And since it involves no rotating parts, it's an added safety feature. And then all the test scenarios or test cases are reproducible worldwide, and they're identical worldwide, and so on. And now, what's interesting is my test setup is ready to be started on, but right now, this will not be covered in this webinar, this live training session. Please stay tuned to our next session where we show you a test case where we turn on the system with high voltage and make the high current to flow through the system with different test cases, steady state test case and the dynamic test case where we change the speed, where we put the emulator in block rotor test, and also stimulate some fault scenarios and so on. So thank you so much for your attention. If you have any questions, I think you have already submitted some questions online, so we'll transfer to answer them one by one. Thank you so much.
Okay, thank you, Nagindra, for this nice presentation. We already received some of the questions. We'll just start by reading the first question. I think you can answer this directly. How do we make sure that all of the control interfaces that are given with this certain inverter are compatible with our EMA? Because does the EMA somehow have to control the inverter as well?
No, the inverter control is completely independent of the EMA control. So the inverter control is completely done by the customer control system. So the EMA acts just as an external motor replacement and doesn't need to communicate with the inverter control system at all. I hope that answers the question.
Okay, thank you, Nagindra. And the next question would be, can we also integrate climatic chambers in our test equipment, and do we also have vibration rigs?
Yes. In the standard test configuration matrix, what we provide, it also comes with a climatic chamber and also the coolant conditioning systems and so on. Yes, that's possible. Vibration rig test setup is not our standard at the moment. Yeah, I hope that answers the question.
Then the next question would be for emulating different types of E-motors that you showed already.
Yeah.
What are the changes that are necessary to make them run on the emulator?
Okay, so there is no physical motor available present here. It's just all models are software. So a 5-second reboot is sufficient. And if the number of phases changes, the testbed configuration must also be changed, of course, from 3-phase to 6 phases. That I mean, if we are sticking with just a 3-phase system, and then if you want to change the motor model, the motor itself, all we need to do is pick a second option and reboot in 5 seconds, and you should be ready to test the next motor. I hope that answers the question.
Okay, thanks Nagendra. And the next question would be, up to how many phases can we already emulate motors, for example 6 phases or 9 phases?
Okay, we are currently offering the emulation capability for 3-phase system and 6-phase system. If the market requirements change for more phases, we will come up with suitable solutions for that as well. But at the moment, the possibility is for only 3-phase and 6-phase.
Okay, thank you. And one last question that we received is the following. Can we test an inverter with a power rating which is higher than the battery emulator? For example, the inverter has 250 kilowatts and the battery emulator has just 160 kilowatts.
No, this is not possible. So it's always needs to be taken care that the battery emulator power capacity has to be considered. So even if the inverter is capable of handling more power, the safety limit now comes from the battery emulator itself.
But this would mean that we at least can test this 160 kilowatts.
Of course, yes, that's possible, up to 160 kilowatt. So that's the thing. So these battery emulators are also configurable. So we offer solutions for 160 kilowatt, 250 kilowatt, 500 kilowatt, and 320 kilowatts. So yeah, up to that limit one can test, yes, of course.
Okay, thank you, Nagendra. And that's all of the questions that we received. If you, the audience, have further questions, please don't hesitate to contact us by any means, and we will try to help you with your to find the right solution for your problem.
Yep.
So thank you, Nagendra, once again. And with this, I would like to end this today's online training, and I wish you a nice rest of the day. Thank you.
Yeah. Thank you everyone for your questions and for joining us in this live training session. And this is a part of live training series. What we have in the upcoming series is we will cover all the aspects of inverter testing in terms of motor modeling and fault scenarios and so on. So please stay tuned and subscribe to our latest. Thank you.